Hey everyone, welcome to the video on solids of revolution talking about cylindrical shells and finding volumes with that method. We've already been through the disc and washer methods, so if you haven't done those before, make sure you go back and take a look at those. But today we'll just be talking about shells. There's two things we want to do. One is just how do you find the volume with cylindrical shells, but then also kind of a comparison of the disc washer method and the shell method. So we will do a little bit of that. So first question here, draw a skinny rectangle parallel to the line shown, and we're going to draw what it looks like rotated around the axis, and then try to find the volume of that just little shape. And I should mention you should have these shapes right here. So this green one and this yellow one will be referenced in this document, so go ahead and have those out as well. And you may want to take this purple little foam piece out of this green one as we start talking about just rotating this rectangle parallel to the axis. So I'm going to go ahead and draw in a little rectangle here parallel to the axis, and we'll go ahead and rotate that around this axis. It'll look something like this. And usually what we did before is when this was perpendicular to the axis, we would get flat shape, so either a disc or a washer. This is definitely going to be a 3D shape. There's no way to make this flat or fit into a 2D kind of scenario. So definitely taking up space in 3D on this one. But we would get what looks like, kind of this cylinder that's right here, and this is hollow inside. So we're thinking of this as a really thin shell. Usually we call these cylindrical shells. You can think of it like maybe a soup can that has no top or bottom on it. The lid and the bottom have been taken off. Or you can think of it like a noodle that's hollow on the inside. So there's lots of different things you can think of that just have this really thin edge that goes around, but nothing on the inside of that cylinder. We want to find what is the volume, not inside the cylinder, but just of the amount of stuff that we have that's been rotated. So just this really thin outside piece that goes around. What is the volume of just the outside? So if you were doing a can, how much metal would be in that can? Alright, so first thing, we're going to label a couple of these things. So we do have a circle here, so let's go ahead and label this radius R. So I'll go ahead and call that R. And this length of the rectangle, you could call that a couple different things. If you rotate around a vertical axis, a lot of times we think of that as the height of the rectangle. I'm going to stick with that notation here as well. So we'll call this the height of the rectangle. Even though it's sideways, we'll just still stick with height for that one. So I got my radius of this circle, I got the height h there. And the thickness of this material, we can think of that, in this case it would be a small change in y, so you can maybe call that dy for the thickness there, or in other scenarios it might be a dx. I'll just say or dx for that small thickness if you were say going the other way where this can was upright and that was a vertical rectangle instead of horizontal. Alright, so the volume of this guy is, let's think about maybe just slicing this and unwrapping it. So draw what the shape would look like unwrapped. So if we unwrap it, just maybe cut along the edge and then unfold it. And here you can take out those purple foam pieces, like I said, from the green, and actually unwrap it if you want to see what it looks like. It should look like just a rectangle. So you get this rectangle that's kind come out of cutting this edge and then just unwrapping that cylinder. The thickness, same thing. So this will have, a little bit of thickness, not much, right there. So that'll be the dy. But essentially what will happen is we're going to be looking at finding the volume of this really thin rectangle, not very thick going into the page, just that small little dy. But we do have a larger area right here. So there's the dy, that's kind of that depth. The height is going to be, let's call this h. So this was my rectangle that we had. We're calling that the height of the rectangle. So we'll label that h. And then how long is this edge over here on the right? So if you want to think of that as like length or width, you can. So that should correspond with how far we go around this circle, right? That's what got unwrapped. So what is the circumference of that circle? And the circumference of that circle would be circumference. Remember some of your geometry is 2 pi r. So that's going to be the same length over here, 2 pi r. So that's what this shape would look like unwrapped, and sort of the labels that you could put on it that match with the 3D view of that shell. Alright, so what formula could we use to find the volume of that rotated rectangle? Well, the volume of a cube, right, is just this length times width times height, or, height, width, depth, however you want to call those, just the three sides multiplied together. So that volume would be, we'll start with this 2 pi r times h, and then times that thickness dy, or, in the case of the other way, dx. I have at the end, say, or dx instead of dy. It could be either one depending on your scenario. But that is what you're going to get for that volume of that sort of unwrapped shell, and then once it's connected again, it's the same volume, so volume of that shell. If you added them all up, what would you get for the volume? So this is going to be, just an integral, so you can think of it again as kind of integrating that 2 pi r h dy or dx if you need it, and then whatever those bounds would be. So in this case, we'd have a y goes from, say, a to b, or it could be an x if it were a dx, that sort of thing. So this is what we're going to be doing most of the time, is just setting these integrals up that look sort of like this, finding the r, finding the h, putting those in terms of whatever we have here. In this case, it would be in terms of y. For other ones, it might be in terms of x. And then how would you describe the difference between a washer and a cylindrical shell? So there's various things you could put there. One thing for sure, washers are, sort of flat. Shells are not, typically. And they do both kind of resemble a cylinder, but this one is just that thin outside edge of that cylinder, where you don't really have anything kind of inside the cylinder. It's just the very thin edge, and washers are much more flat. You have a much wider band between the inside radius and the outside radius for those guys. So those are just a couple of differences. It is important that you kind of know what the difference in those shapes is. All right. So here's one example that we'll try to get through by the end of this video, and then we'll probably do the rest in another one. So this is what you would see, that green object that you have in your kit. This is sort of the computerized version of that, something you might see in a textbook. And first off, we're just going to go through and try to find the volume, ask ourselves a few questions. So first off, what is the axis of rotation? All right, so just like was the blue one in the disc and washer worksheet, the axis of rotation is going to be right here on the y-axis, kind of runs straight through the middle of this green object right there. through that hole. So y-axis on this one, let's say x equals 0, or you just want to write y-axis, that's fine. Darken in the axis and draw a sample rectangle to rotate, sketch what it would look like. So here, again, we want to do these vertical pieces parallel if we're going to use shells. So this is going to be parallel to the axis of rotation, and we'll get something along these lines. So sort of like that for my shell. And the idea is that now I can try to find what is the R, what is the H for those guys. So this right here will be my R, and this will be my H. All right. So for the R, I should also put in our dx or dy. So this rectangle that's coming down right here, right, super thin in the x direction, so this is going to be a dx. So we want to make sure our R and our H are both in terms of x for this guy. So if we think about what the volume of this would be, right, so this is going to be volume is always the same, 2 pi r times h. We do know this time it's dx, so we'll go and use dx. And then we just need to find what's the value of the r and the h. So the r, right, how far do I go from the axis out to this rectangle? And if you think about how you plot points, right, if I was going to go out here and plot a point, this would be how far I move in the x direction. And that's actually just the value for r is just x, right? I move from the axis, y-axis, out a distance x to get to any point on this curve. Since we want it in terms of x, we can just leave it. There's no need to solve or rearrange or anything. We're just going to leave that as x. The height, on the other hand, right, it's this y on top, oops, minus this y on the bottom. So we're going to go ahead and subtract those guys. And let's see what we get. So the y on top, this is going to be our curve. So we'll say, I'll just use right now yt and yb. So that h is going to be the y on top minus the y on bottom. And the y on top, we want these in terms of x. So it's this negative x minus 3 squared. If I go up just a little bit, you can see that negative x minus 3 squared plus 4. So I'll go and write that in. Negative x minus 3 squared plus 4. So that's my y on top minus the y on bottom. The y on the bottom is always at 0 in this case, so that makes the subtraction easy. So we're just subtracting 0, and that will be our height. It's just this negative x minus 3 squared plus 4 for that h. All right. So that's going to be the volume of this general sample shell, and then we'll do an integral to go and set that up. So let's go and write this in. So 2 pi, the r we said was x, the h is this negative x minus 3 squared plus 4, and then and again that whole thing's times x, so make sure you use the parentheses there, and then we got the dx. And when we integrate, we're going to integrate, x's are going to run from 1 over here to 5, so just from 1 to 5 across all those x values. And then we'll go ahead and compute that out and see what we get. So integral 1 to 5 of this 2 pi x, x minus 3 squared plus 4 dx. And I'll go ahead and calculate that, put it in here real quick. I just plugged it into Desmos real quick here, and we get 201.062 if you round to 3 decimal places. So if you just want to put that in, you get 201.062. All right, so that's the basics of shells. Next time we'll kind of take a look at difference between discs and washers and shells, and kind of make some comparisons there, and look at a few more examples.